Hello everyone, and welcome to our presentation, where we introduce an improved approximation algorithm for the uniform cost-distance Steiner tree problem. But before getting to the precise definition, let's first go over the motivation for studying this problem. It appears mainly in routing, particularly on integrated circuits, where we are trying to minimize the total amount of wire used in a net connecting a number of terminals while controlling the signal delays from a source to its sinks. This requirement may be abstracted as trying to find a Steiner tree connecting a number of nodes, which is both light and shallow. Light Steiner tree is one that has the sum of its edge costs as low as possible, such as this minimum cost spanning tree on the left, while a shallow Steiner tree is one where the path length from the source to its sinks is as short as possible, like this shortest path tree in the middle. Now, ideally, we are looking for a solution that could satisfy both criteria simultaneously, like the one on the right. However, this would not be possible in every case. For example, if we add an additional node in the middle on top, then we can't be optimal in both respects. So in order to be able to select uniquely from a set of candidate solutions which meet a compromise of the two requirements as good as possible, we have priorities on the terminals which determine how critical their timing constraints are. For example, if the node here on the bottom right has high priority, we may want to connect it directly from the root. Whereas if its priority is lowered, then this minimum cost spanning tree might be better. Formally, the shallow light Steiner tree problem takes as input a graph, a root vertex, a set of terminals, edge costs, edge delays, and delay bounds for the terminals. And the task is to compute a minimum cost Steiner tree that respects the delay bounds on the terminals. And now the cost-distance Steiner tree problem arises as the Lagrangian relaxation of this problem, where now the constraints disappear and the path delays from the root to the terminals instead appear as additive terms in the objective function in addition to the regular cost of the Steiner tree. These appear with multiplicative coefficients called the Lagrange multipliers, which we refer to as the delay weights, which are taken as input for the cost-distance Steiner tree problem for the terminals instead of the delay bounds. The reason this problem is important for us is that it is used in an oracle in timing constrained global routing, where we have many trees with mutual delay dependencies, such that the problem is complex and we rely on relaxation in order for it to become solvable. Previous known results for the cost-distance Steiner tree problem include an O log of t factor approximation, an omega log of t in approximation, and a 2.87 factor approximation for the uniform case, that is, when the edge costs are equal to edge delays for all edges throughout the entire graph. Now, in this talk, we will mainly focus on the uniform case and first prove that it remains NP-hard in the case where all vertices other than the root are terminals, and then improve upon the constant factor approximation. So notice that the uniform cost-distance Steiner tree problem contains the regular Steiner tree problem as a special case when setting the delay weights to 0. And this directly implies that it's NP-hard. However, if all the vertices other than the root are terminals, then this would render the Steiner tree into a spanning tree whose problem would not be NP-hard anymore. What we show here is that in the general case where delay weights are not necessarily 0, our problem remains NP-hard in the case where the root and the terminals constitute the entire set of vertices for the graph, showing that the hardness also stems from the dual nature of the objective function and does not rely solely on the Steiner tree problem. And the way we do this is by reduction from satisfiability. So for a given formula, for a given Boolean formula phi in conjunctive normal form on variables x1 to xn, we construct an instance of our problem based on this formula. And for that, we use a gadget consisting of a pair of nodes for each variable, one representing itself and one its negation, connected to each other by an edge of length 1, each connected to the root by an edge of length 2, and we give both of them delay weights equal to 0. For each clause, we have a separate node with delay weight a positive constant w, connected by edges of length 2 to the nodes representing its literals. Now, one may verify that a good solution will always pick the edge of length 1, and these clause nodes will have a shorter path to the root if at least one of their literals has a representing node which is directly connected to the root. And these are the literals that we interpret as being evaluated to true. So we may show that phi is satisfiable if and only if this instant has a solution of objective value at most a certain amount, proving that the uniform cost system Steiner tree problem remains NP-hard when all vertices are either the root or a terminal. Now, in order to explain our improvement upon the constant factor approximation, we first review the algorithm providing the previous best constant factor. And it makes use of a bicriteria approximation algorithm. And as input, it takes the usual instance along with a positive epsilon, which is at first chosen arbitrarily or provided in the input and later tuned to find the best approximation bound. What is done here is a beta approximate minimum Steiner tree is input to the bicriteria algorithm, which starting from the root goes around this tree in DFS order. And whenever path lengths in our partial solution exceeds a factor of 1 plus epsilon, the direct distances in the graph, the shortest root to terminal path or root to node path is added to our solution. And since we add shortest paths, our partial solution, the set of edges that we are keeping may not remain a tree. And that is why at the end, we must output a shortest path tree within this set of edges. Now, by condition in the algorithm, we have that the tree path lengths in this output solution must be bounded by a factor of 1 plus epsilon times the direct distances in the graph. But what is also possible to show is that the total sum of edge costs of the solution is bounded by a factor of 1 plus 2 over epsilon times a beta approximate Steiner tree that was input to the algorithm. So if if C of SMT is defined as the cost of a minimum cost Steiner tree, and D of SP is the delay of the contribution to the delay term in the objective function of a shortest path tree, then since each one is the minimum for the respective term in the objective function, then their sum must also be a lower bound for the entire objective value attainable by any solution. However, they might not both be able to be minimized by a single solution. And now the solution output by this bicriteria method will be bounded by a factor of 1 plus 2 over epsilon times beta, that of CSMT, plus the factor of 1 plus epsilon times D of SP. By setting these two factors equal to one another, we may obtain a single approximating factor for the entire expression. and solving for epsilon, we get such an approximation factor where beta is the approximation ratio for the Steiner tree problem, which for Ln of 4 plus a small amount evaluates to 2.87. Now, you should notice that throughout this algorithm, the delay weights of the terminals were not made use of. And this is exactly what we take advantage of to obtain our improved algorithm. So what we do in our algorithm is first we choose a threshold mu for the sum of the delay weights of all terminals using a given edge on their shortest path from the root. And we begin with an approximate minimum cost Steiner tree, going up in a bottom-up fashion in reverse topological order, starting from the leaves. We cut off subarborescences at each node where the terminals beneath it have a sum of delay weights exceeding the threshold. And then in the end, we reconnect these cutoff clusters back to the root by shortest paths. So in order to describe our algorithm in more detail, after having fixed threshold mu, the first thing we do before the other steps in the algorithm is first we have to identify heavy terminals. That is, terminals that have a delay weight above the threshold. So that would be these two terminals here in this instance. After identifying them, we may simply connect them directly to the root by shortest paths, and then set them aside from the rest of the algorithm so we don't have to deal with them anymore. So that now we are left with a number of terminals, each with a delay weight of at most the threshold mu, which we may connect together by an approximate Steiner tree. And now before the main part of the algorithm is executed, we apply a pre-processing step on the graph, on the underlying graph, in order to make this initial solution binary and all the terminals into leaves. And we may do this by adding dummy vertices and edges of zero weights and costs as such. And for easier viewing, you may see the expanded tree on the right, for which we now start from the leaves, go up in reverse topological order, and start cutting off wherever the threshold is exceeded by the terminals beneath the nodes, update the values on the edges, and proceed in this manner until we have a number of disjoint clusters and possibly one connected component containing the root, which may possibly have more than one outgoing edge from the root. And now we have to reconnect our cutoff tree by shortest paths. And in each cluster, we make a choice of one of the terminals to connect the rest of the cluster through to the root. And this choice of the best terminal to serve as a port for the other terminals inside its cluster to the root is made such that the computed contribution of this cluster to the objective value is minimized. So now to analyze the value of the solution that our algorithm outputs, we point out that when a vertex V is visited in the bottom-up cutting procedure, any child U of V will have all the terminals beneath itself have a sum of delay weights bounded by the threshold mu. That is because otherwise the edge between U and V would have been cut off before the vertex V was visited. And now, since the root of a subarborescence may only have at most 2 outgoing edges because of the pre-processing step we performed to make the tree binary, for a terminal cluster T prime that is not a heavy singleton, which does not require a subarborescence to connect it since it's only one terminal, a multi-terminal cluster T prime will have a sum of edge delays at most 2 times the threshold, 2 mu, since the right and left subarborescences of the root of the entire subarborescence connecting this terminal. Each may carry at most mu sum of delay weights. This enables us to prove a lemma bounding the contribution of a single cluster to the objective value. So for a terminal cluster T prime connected together by subarborescence A prime, which may have empty edge set if the cluster is a singleton. Having made the optimum choice of portal to be connected by shortest path P to the root, thus connecting the other terminals in its cluster through itself to the root. We have for the tree obtained by the shortest path union this subarborescence, that its contribution to the objective value will be this expression here, 1 plus mu times the sum of its edge costs plus a factor of 1 plus 1 over mu times the contribution of a shortest path tree, or weighted sum of distances from the terminals to the root. In order to see this, instead of the optimum choice, we first make a random choice of terminal within each cluster with a probability for each terminal proportional to its delay weight. That way we could compute the expected value of different contributions under this random choice, and this will help our analysis further along the line. So if capital W denotes the total delay weight sum of all terminals throughout the cluster, and W sub V the sum of delay weights of the terminals beneath a node V inside the subarborescence, we have that with probability W sub V divided by capital W, the chosen port will be in the subarborescence rooted at V. And the sum of delay weights of all terminals using the incoming edge to vertex V on their shortest path from the root will be capital W minus W sub V. And with probability 1 minus that, the sum of delay weights of all terminals using the incoming edge to V on their shortest path from the root to themselves will be just W sub V, because the port was chosen from outside the subarborescence rooted at V. So if we define the contribution to the delay term of the objective function of edge E as its cost multiplied by the sum of delay weights of all terminals using that edge, we have computed the expected value of this sum of delay weights here, which is at most mu. And so we obtain that the expected value of the contribution of an edge to the delay is at most mu times its cost. Extending this definition of delay contribution to sets of edges and summing overall edges within a sub cluster A prime, we get that the expected value of the total delay contribution of a subarborescence A prime is at most mu times the total cost of its edges. We also added shortest paths that we need to analyze. And we have that the expected value of its delay contribution will be just the weighted sum of distances of the terminals to the root, which is the contribution of the shortest path tree, connecting the terminals in that cluster to the root, and as minimum possible, by the way. And the expected value of its cost will be missing a factor of capital W outside the sum, so it will be 1 divided by capital W, the same sum. But since capital W is larger than mu, we have that this will be less than 1 over mu times the delay contribution of the shortest path tree. Now, since the choice of port terminal was made to be optimal, we have that the contribution of a cluster to the objective value will be no more than the sum of the expected values on the random choice. And luckily, with the choice of probabilities proportional to delay weights, they sum up to exactly the desired bound in the lemma. And now summing this over all clusters in the initial solution, we obtain this bound for the entire solution output by our algorithm, which has a factor of 1 plus mu times beta times the cost of a minimum cost Steiner tree, plus a factor of 1 plus 1 over mu times the delay contribution of the shortest path tree. Now notice that in our algorithm, we only require one computation of an approximate Steiner tree, approximate minimum cost Steiner tree. We need shortest paths from all terminals to the root, which may be obtained by running Dijkstra once from the root, and then quadratically many arithmetic operations in the number of terminals to identify the optimum port within each cluster for all of the clusters. And therefore, the runtime of our algorithm is also quite feasible. Now, setting these two factors equal to one another, as in the previous method, but now with one of our factors missing a 2 here, we can obtain an improved approximation bound of 1 plus beta, where beta is the Steiner approximation ratio, which for ln of 4 plus a small value evaluates to 2.39, which is a significant improvement over the previous 2.87. And with that, I conclude our talk and thank you for your attention.